Okay, let's get started. I don't know how far people can see me, so apparently the streaming is working, so welcome to Big Wide World out there to today's seminar at the Untitled Institute in Cambridge, which is part of the Data Linkage and Anonymisation program, and it's hopefully the first seminar which we can stream through. My name is Peter Christen. Robin, the seminar coordinator, cannot be here today, but if you are out there and you have any questions, send them to me via email, and I'll try to relay them to Tom. Okay, so today's speaker is Tom Dalton. He's from the University of St Andrews, and he's a PhD student second year, I think, at the moment, working on developing data generators for data linkage. And this is part of different projects, Digitizing Scotland. And you can maybe talk a bit more about what the background of the project is.
Yeah.
Over to you, Tom.
That's good. Thank you very much, Peter. Today I'm going to be talking about how we go about within our project setting up and generating synthetic data, and our main aim here is about how we evaluate data linkage, and we're kind of taking inspiration from what could be described as a good linkage evaluation model. So as Peter alluded to, this is part of wider work of a project called the Digitising Scotland project. The main part of the funding for the Digitising Scotland project is goes toward the transcribing of vital event records from when historical recording in Scotland moved over to registrars in 1855, and those records up to 1973. Quite a lot of these, as you've probably seen if you've ever tried to look up the census records of relatives, are written in very spidery handwriting and are quite difficult to read often. So the majority of the budget, as I mentioned, is going towards the actual transcription of these. And then our group is also focused on how we go about linking together all these records and building a large family tree for all of Scotland. And then the question that this particular seminar pertains to is, how do we actually evaluate the data linkage approaches that we develop to do this? So as I've alluded to, we're looking at using synthetic data for that purpose. This is inspired by real-world hand-linked gold standard data. So the idea there is you have a data set that exists in the real world, and somebody at some point has sat down and they've linked that data together by hand. These do exist. There are a couple we have access to, but notably with each of these, they're normally very small. You don't normally get anything of more than 20 or 30,000 people. And they also have their own inherent errors. I was chatting to a woman who has produced one of these a couple of weeks ago at a conference, and she kind of was quite apprehensive when somebody described her data as gold standard. And she was like, no, there's far too many errors in here for it ever to be used as a kind of evaluation method. So there's those real inherent errors. And also, in terms of limited size, there's also limited availability of these. So there's not a massive number of them, and to actually generate them takes years and years of manual labour. So the reality of having synthetic data really serves to meet several of those issues. You have the fact that if you have generated a population yourself, you know all the information you have generated, and therefore you know the underlying truth of this whole population. It gives you a perfect gold standard, and this is really important when you come to evaluation. So if you're assessing your gold standard against hand-linked data, and that in itself has errors, if you link something in your real-world data, but the historian who hand-linked it says, oh no, that wasn't a link, you can get a disagreement there, and actually in the places where the historian has made errors, your evaluation will actually indicate that your linkage approach is not doing as well as it actually is. Other benefits of synthetic data is we're not just tied to the populations we have. We can model lots of different characteristics in synthetic populations. We can vary the sizes of those, and also we can generate hundreds and hundreds of these, and so we have the ability to test against all these different kind of variations. And another little side point to note there is a known level of corruption. Real-world data, we know, has corruptions in it. We know there's misspelling of names and people haven't written things down correctly, or data has not been recorded. However, we don't know how often names are misspelled and these different things. So if we have synthetic data which represents an absolute truth. There is then the option, by the use of other software, to introduce corruptions in a controlled manner to the data sets we want to practice linking. All of this boils down to, at the end of the day, many of us are working with what could be described as data-driven problems. We all need to evaluate them, and the thought here is, what synthetic data can we use to better evaluate the solutions we are finding to these problems? Throughout this presentation, I'm going to talk through two different population models we've developed. I'm going to talk first about the one which is currently available and is being used by some people for synthetic data. It follows what could be described as an event-driven microsimulation approach, and was work that was undertaken by myself and Victor Andre, and was actually undertaken as part of undergraduate summer research placements a couple of years ago. What I'll then go on to talk to is what's forming the wider body of my PhD, and that is the verified population approach. This seeks to address some of the concerns we had with the initial approach, which I will explain as we go through. Okay, so the OPM, or the organic population model. So the general approach here is that the user sets a set of input distributions that tell us different things, from the initial size of the population to the rates at which people should die, and we'll go into a bit more detail with them in a minute. The idea is the model then initialises a population, and then there's a number of events that happen in this population that are allowed to occur and are handled, and the end result is a population over a temporal period of time that can then be output into whichever format or usage that we desire. And then we also have, throughout all this, we're logging different things that we're doing, so we have some method to actually evaluate the synthetic populations we are creating. So this is the range of inputs we have on the first model. The first thing you'll probably notice is there's quite a lot of them, and they're quite varied. As we go through, I will allude to some of these, and as we discuss the second model, we will discuss about what has changed with these and what issues we ran into. So this is an example of a couple of those inputs. The top one, the easiest way of reading these tables is to look at the top row, and this effectively says this is a data distribution, and the value, when I ask for a value from this distribution, it will be a value between 0 and 336,525, so that's the number of days in a normal human, or the maximum number of days in a 100-year span. As these numbers get bigger, and I ask for a value from 1600, it's more likely that people will live to around this period of time, and less likely that they will die very young. And the same idea is represented with females and males at age of marriage. Again, that ages of marriage tend to be lower, and not as many people tend to get married at older ages. And we, as I have noted, have the opportunity to change these over time within our simulation models. So this is going to be a bit of a walkthrough of how actually this model runs underneath. I've alluded to the fact it's an event-driven model, and that will start to become apparent as we go through. So, as we've already mentioned, we've taken the inputs from the user chooses the start date, we then choose how big this initial population is going to be, and then the first thing the simulation model does is we decide the ages of the people in this population at the given start date. Once we have decided on how many people there are going to be and how old they will be at the start date, we can work out a date of birth for them. We can then make a birth event, and we can insert it into this blue thing, which we're going to treat as a queue. So, for example, we have a person who we have decided will be born in 1670, and in this population we're going to talk about for the next 5-10 minutes, there are 3 people, and you can see as we're inserting people, we're inserting them in data order. So the idea is that we take events from the head of the queue, and then each of these events in turn is handled and will result in new events. So as we're handling these events, we're going to do certain things in our population to perform these events, and each event itself will likely cause an additional event which occurs. So the first event we've got in the queue is a born event. So the first thing we do when we take a person out of the queue is we would create this person, and then we make a couple of decisions about what this person's life within the simulation is going to look like. We will first of all decide what kind of partnership they're going to have, and then we would set the date that partnership will happen, and we will insert it into the queue. So the example here is this person who is going to be born will get married on this date, and then the next thing we decide for this person is when they're going to die, and we insert that as an event into the queue. And then again, and then we've got another born event at the head of the queue, which we're going to take out. We'll insert a marriage event for that person, and then we'll insert a death event for this person. So this is it's quite an iterative process. The event at the head, you always take the event from the head of the queue, and that always has a couple of resultant actions that we do. So the next thing at the head of the queue is we notice we've got marriage event. So marriage events are handled slightly more complicated to handle than birth events. So I'm going to introduce this concept we have within the model, which is marriage queue. So the idea is that we put people, when we find people in our event queue who need to be married to other individuals, we place them into the marriage queue, and once every so often we look through these queues and then we pair people together appropriately, which is exactly how the real world works. So we take this first person and we add them down into the queue. And then we take the second person who just happens to be a female and also add them into the queue. So now that we've got two people in the queue, we can simulate what we would normally do in the model. So normally in the model we'd expect to have dozens of people in these queues, and so we'd only be running it every so often. So as we come to partnering individuals, this is something we do once a year. We iterate over the queues that are here. We partner together the people who are eligible. So the only real restrictions we make there is that the age bounds on people getting married are within a reasonable frame, and then there'll be a set of resultant events that get created because of this. So when we partner individuals together, we decide on when that relationship will end, and we also decide on if there will be any children or whether there will be a first child in that relationship. So when we've taken these two people out of our marriage queue, we've then decided that this marriage will end at this given date, and then we also insert what is called a birth event. So a birth event is slightly different to a born event, because a birth event pertains to what we do with partnerships, and a born event pertains to individuals. And yes.
How do you determine? Is there some sort of probability structure? Or?
Yes. So if I jump back to the inputs we had before, so there's probably a dozen, within these 25 distribution inputs, there's different things that tell us what am I looking for. So we've got things that tell us at what age people get married, and then the people being paired together is it's just an iterative process, but then the decision on how many children for people to have is satisfied by the number of children that would be expected to be seen in a marriage. I'll talk a bit more at the end about the way in which these are structured, and also how well they interact or don't interact with the data we actually see out in the real world. I think jump forward to where we were. So we've inserted a birth event and we've inserted a born event, and they're different because of one being pertinent to partnerships and the other being pertinent to individuals. So again,
if one was supposed to be married in 1689 and the other in 1690, how could they marry each other?
So this is an issue that we run into in the underlying model, the fact that when you place people into queues, to an extent that kind of issue is mitigated by having larger numbers of people in the population. But there is situations where you get people being left in a marriage queue, for example, never being married off, and therefore that leads to you not being actually able to meet the underlying statistics that you have identified. So that is a limitation of this model and something that we sought to address in the second model. Yes. So again, we're handling a born event, and this time we've actually decided this person is going to be single, and so we've just inserted a coming of age event into the queue. This is something I'll explain in a minute when we get to handling an event. Again, for the person being born, we've inserted a death event, and then we've got a birth event at the head of the queue for the first time. So this time, because this pertains to a partnership, we decide if there's going to be another birth, and if there is going to be another birth, we insert it into the queue. These relevant events into the queue, which we can see happening here. Again, this starts to get quite self-explanatory, so it will move reasonably quickly. And so for this individual, we've actually not inserted a partnership event because we've inserted a death event, which happens shortly after birth. And again, as we handle these different events, and then when we come to handling death events, the thing that we do here is simply we do some logging in the underlying population and we remove individuals from the queue. Again, and so I'm going to start moving slightly faster here. We're adding new types of events to the queue, but these again are just events that are resulting from the events we have already handled. So before when I was chatting about the different levels of complexity we have in the model, and the different kinds of relationships we model to introduce complexity in the genealogical structures, we don't simply have the idea of marriage, we also have the idea of cohabitation, and we have an idea of singleness as well. So different people will get placed into different queues depending on the kinds of relationships that we're going to place them into. So for example here we're going to handle a divorce event. So when we're handling a divorce event, we have the option, we have two individuals which we then need to decide what to do with them. So in this example we're going to decide that number one will get married again, and this is supported by an underlying statistic again to tell us how often people will remarry after divorce. And then the other individual we've placed at the head of the queue as we've decided they won't remarry again. Interestingly, we've now got an event that is happening in the past. So the thing with coming of age events are that they occur 16 years after the individual's birth. And so for this individual, it's been set as 16 years after birth, and because it is in the past, it has been put at the head of the event queue to be handled next. So when we take a coming of age individual, we simply place them into the singles queue, and what we do with the singles queue is we use that to introduce further genealogical complexity by using them in further other relationships with individuals that are within relationships within these queues. So in real world terms, we're modelling the idea of somebody having an affair, and so you could end up seeing a population structure where you have illegitimate children. And now we've arrived at a point where we have a marriage event, and again we place them into the marriage queue, and we place this individual into the cohabitation queue. Now this very much lays out the issue that people were touching on before, of we have people in these queues and we're not actually able to perform the events that are required. So when we actually ran this model at scale, that didn't actually turn out to be a massive issue, and for the most part there was a sufficient number of individuals that distributions would be met for the rates of marriage and the rates of cohabitation. But nonetheless, we have a fundamental issue underlying in the model, which we will talk about how we address later. Here, and just to conclude the event, we simply have the idea of removing deaths, and when we remove people at the point of death, we also remove them from the relevant queue because they're no longer eligible to be there. And here we can say that our model finishes in 1740, and therefore we have no need to handle this final event. And so we would see one person surviving the population in our example.
Presumably the distributions are time inhomogeneous, so that you gave the coming of age as age 16 back in the 18th century. That would really be the case, or whether it would be younger,
Yes, so the actual 16 I've referenced is simply what we would consider, but actually that's just a figure within the model which is configurable. And so if somebody wants to set the age as much lower or much higher, that's something that we're allowed for. Okay, so as we've kind of touched on throughout, this model does have a few problems which we are going to talk quickly through what happens. So before I showed you a big list of 25 inputs. Now with 25 inputs we often came up against the issue where we could meet perhaps 10 of these inputs, but some of these other inputs weren't able to be met. So for example, if I show you this graph, and this shows, so the purple line on this graph is what actually happened in the population, and the green line is what we wanted to happen in the population. So for this matter, we actually managed to meet very well the set of events that we wanted to happen. So just to note, this is cohabitation and the numbers of cohabitation and the length of cohabitations that occur. So if I next show you this distribution, which again pertains to the number of children we expect to see in cohabitation relationships. So we've placed a peak here of 3 children being born into each type of cohabitation relationship. But actually, if we jump back, we notice that the majority of relationships have ended within 5 years, and the likelihood of having 3 children in that small period of time is effectively 0. And so we end up with the values in one distribution preventing us from meeting a different distribution. And so this is one of the biggest issues we faced with this first approach.
Sorry, do all cohabitations lead to children?
No, not in this first model. For the data I've ran it with here, it appears that they did, but that isn't a required necessity within the model.
So when you had that list of probability distributions, it was all just single, univariate distributions? You didn't try and do any multivariate or conditional?
Within this first model, yeah, they're all univariate, whereas in the second model, we start to see different conditionals based on age and variation over the course of life. So a couple of other issues we faced with this model. I showed you the death distribution before, and the idea, and you've seen as we've walked through the model, the idea that when somebody's born, we decide when they're going to die. And that means that for each year, we assume sparsity of input data. We don't expect someone to have sat down and written data out for 200 years. The idea is somebody will insert data for every 10 or 20 years, and that will be used in the model. So when we come to something occurring like extraordinary events, when you've had data which says people born in this year, they will die following this distribution of different ages. If we want to say an earthquake occurs in 1900, to induce the spike of death rates, you actually have to change all the preceding input distributions, and it would also require that they be done every year for the previous 100 years. So that's a severe limitation to this model if we're wanting to model such things. The other thing is the quantification of inputs. So we kind of spoke about how we modelled a number of children that occur, we modelled a number of people in a certain type of relationship, and then we choose the number of people, in fact children, to be had in that particular relationship. Now if we said something like total fertility rate that we see in the real world, that's a very hard jump to go from what we're actually modelling here to what we actually see in the real world. So actually how we quantify the inputs we're giving our model is quite difficult as well. And then probably the biggest issue in terms of convincing other people to use this is telling them that the population that you've generated for them is actually the same as the population they asked for. And although I showed you a few plots, and we produced plots for every input distribution for every period of time that it has been adjusted for, you end up with 300 or 400 plots. People don't really want to have to trawl through 300 or 400 plots, and also there's a question of that line looks reasonably close, is that close enough? So obviously we need some much more involved statistics than what we were currently doing in this model. So this moves us on to the verified population model. And so at the outset, we set ourselves a bit of a spec, and so this is what our idea effectively was. Our aim is to produce synthetic populations, and this we have summated as a graph structure, a tree structure, and this represents the true linkage of the population, the actual truth that happened. And from this, we want to produce event records, or in our case, vital event records. But this could be your GEDCOM format, or to your database, or whatever different forms of data output that people actually look to use. We also want the input, rather than to be based on these rather ill-determined input distributions like the old model, to be based on some statistics that you could go and find if you went to the ONS website and started looking for information about real populations. And I'll take us through those input statistics in a moment. Fortunately, there's only 5 in this model, which means we won't be here all day. And then the other really key important thing is that the populations we produce are statistically verifiable. That the input statistics given are the same as that is seen in the produced population. And obviously it's important that we're choosing inputs there that aren't simply focused on matching the mean and the variation, but also looking at the nature of the inputs and therefore the ways which they should be statistically analysed. Other little points that we make about the statistical verification is the idea that, which this is something we haven't properly looked into yet, is the idea of verifying our population against unseen statistics. So the idea is that if you can extract statistics from the real world and you're modelling based on 5 of them, there's other statistics that you would expect to be borne out in your models that exist in the real world population. And so being able to test against these. And another idea we floated on, we're currently chatting with a couple of historians about, is the idea of a Turing test for population. So the Turing testing, its initial idea is the idea of can you tell this computer I'm talking to whether or not it's a human or not, whether or not it's a computer or not. And the idea here is if we give a historian one of our synthetic populations, would they be able to tell it apart from the real thing, the real data that exists in the world? And so that's something we're currently having back and forth with a few historians about. Okay, so this is an overview picture of the verified population model. So the idea, which has kind of been summarised already, is we have a set of input statistics. We follow some rules to produce a population graph, and then this population graph that we produce, we get some output statistics from, and we compare these two. And if this passes, then we move on to the other things down here.
That's right.
It's working. It's working.
And so the other important thing to note here is in this population graph, what we're actually interested in is the genealogical structure. So especially in our linkage domain, the foremost thing that we want to be certain of first is that the genealogical structure we've produced is correct before we go on to apply things like names and locations and occupations that, although are used in data linkage, they rely upon the underlying structure being correct to be able to properly apply them. So for example, with surnames, you want to be assigned the carrying of surnames at the point of marriage, prevent children, and all these kind of things will land in the underlying structure. Once we have, as we call it, annotate the graph which we have produced, we're then able to create vital event records. From the vital event records, various then approaches that exist to or being developed that corrupt data, corrupt the data so that it's more like what we perhaps see with the errors in the real world, and then at the end of all this we end up with our birth, marriage and death records, which we can go away and do our linkage on. Once we've done our linkage on them, we can then come back to the initial graph that we had and go, here's the absolute truth, these are all the links that should be there, the links we found, are they the real links? And so we end up with an evaluation method that comes back from certain. Okay, so most of what I'll be talking about over the next part of end of the presentation is the stuff that comes around this blue cog, how we actually generate this genealogical structure. So the thing that I'll be chatting through as we do that, I'll first talk about what we term as population integrity and the initialisation of the population at the beginning. I'll then talk through the simulation approach and the self-correction work we do with the input statistics. And then I'll talk about the validation approaches we take to actually say whether or not our population is lines up with the input statistics given. So you probably notice that a lot of these inputs are what I put up on the board before, and for the greater part we got rid of most of them. So the idea here was that we wanted to have as few inputs as possible but expressed as much as possible. So for example, the ordered birth rates that we have down here, which I will show you an example of ordered birth rates, an ordered birth rate table in a minute. Ordered birth rates allow us to model a collection of things, for example, family size, the rate at which women of different ages have birth, and the summation of an ordered birth table gives us age-specific fertility rates and also total fertility rates. So some of the things we've been touching on as we've gone through about what the old model didn't do, the aim of this model is to be able to have these input statistics that are highly expressive, but also in the design by being able to find input statistics that combine a number of different things. By all these things being modelled in a single input distribution, it isn't possible for the input distribution to clash with itself, and therefore you defend against the issues that we were demonstrating with the previous model. So if I was to show you through the 5 input distributions that we work with. So the first one we use to model death is something called life tables. So these exist in the real world. Often if you ring up, so for example by insurers to work out the likelihood of death for health insurance. So these things work by saying, for example, an individual aged 1, the rate of, so people aged 1, the rate at which they die in the next 1 year is 0.00945. And again, as we get further up the table, we can see that people aged 100, the likelihood of them dying in the next year is near to 90%. The other good thing to note about this is that we provide one of these for every year. And so rather than assigning people's deaths to happen when they are born, each year as we step through our model, we consider this table, and we can then determine how many individuals are to die in the given year. This does mean that we're doing slightly more computation than the previous model, but it does. But it means that we are able to model things in a lot more detail, and also to allow for different things such as wars or earthquakes to appear in our model without having to really struggle to produce those. So this is an ordered birth table. So in a sense, it's very similar to the first table I showed you, but it is in 2 dimensions. So the way of reading these tables is to say, so for example, for a female aged 17 who has had no previous children, the rate that she would give birth in the next 1 year is 0.038. And so these are all statistics that we can actually apply to cohorts rather than to individuals. So, and which we'll come on to discuss a little more in a minute when we work through the approach of this second model. The other thing I noted when I was overviewing this section, these rows sum to the age-specific fertility rate for women aged 15, and then the summation of these rows times multiplied by the difference in each row, so the number of years each row represents, gives you total fertility rate. So at this point we're actually able not only for people to have a good feel of the data they're giving to the program, but a set of rules which could allow us to generate this table based on somebody saying, I want to see a high fertility rate within the population. And the other thing that I've touched on is that this table, along with separation, can be used to control family size within the population. This is quite a simple table and has survived in more or less the same form as the previous model, apart from it also considers different ages. This concerns things such as singleton births, twins, triplets, quadruplets, and the age of women when they have them. This is different from the event-driven statistics that we've just been looking at by the fact that these rows all sum to 1, and therefore for each year when we're considering women aged 20 to 24 who have children, the vast majority will have one child in a pregnancy, and with reducing numbers up until four children, where not many have quintuplets in a given year. This is how we go about modelling partnering. So something else to mention when we're looking at ordered birth is that this table controls the age of women when they're having children, and therefore, because we're talking about the genealogical structure rather than the social structure in this part of the model, it also tells us the age at which people are getting partnered together based on this first column. So then we move into partnering. So at this point we've decided which females are going to be partnered together and which females need partnered together for the fact that they have to give birth. And this is a crossover table which allows us to select the males to be partnered to the given females. So if we have female ages on this row, for example, women aged 25 to 29, marry men in the bracket aged 25 to 29 most often, and then this distribution has a high point here and tapers in each direction. And then this is the final input we have, and this is how we go about separating partnerships. So this actually is another event-driven statistic in the same way as death was. So in death we were talking, with the life tables we were talking about, in the next year will this individual die, whereas here we're asking the question, will the next child finish this marriage effectively? And so these are the rates at which the marriages end in between children. And so because again we're focused on the genealogical modelling here, rather than focusing on the ages of individuals, we're focusing on what's happening within the partnerships. Okay, so when we're initialising the model, we are given a start date by the user, but when we're given a start date, we have this idea of population integrity. So this effectively is, given the output format, how far back in time do we need to go to get all the data that pertains to somebody born at the start date? So this is dependent on whatever desired record output format we're using. This is an example from the current domain we're focused on, which is a death record. So the example here is that if we have somebody who is alive at the start date of that has been given, the piece of information that will appear on their birth record that we need from history is the mother's maiden name, which in turn is her father's surname. And so even if our population model for the user starts here, for us, it needs to start all the way back here. So this initialisation phase, we have a certain amount of known information, and so we have been given from the user start date, and also how large they desire the initial population to be, and from our output format we know what our earliest reference is, and then the user also provides birth rates and death rates to be used before the model begins. So for example, we can say the size of our population at the start date will be this, and then we can therefore work back to say the size of our population at the beginning, our beginning, gets very confusing when you have two beginnings, will be this. And so we then move into a different screen, And so this is the idea of the total population just before our true beginning time that we're talking about. In here we have odd people that exist hypothetically. Nobody exists in that population, but we know there's this many people. So we then start to go to step forward in our time model, and so we can say, so normally each year in our population model we would say, we take the women, we look at how many they are, we decide how many are to have children, and then we partner people together and handle all the different things, which we'll go into in more detail in a minute. And so, although when we grab these hypothetical individuals, there's nobody to give birth, but because we know what our desired birth rate is and we know what our hypothetical population is, we can begin to create individuals in the population model. And as we step forward, we have more and more individuals being created. So the 250 line here is the point in our model where we want to have all the individuals having their grandfathers, so that we have access to the mother's maiden name. And so as we're working forward, we're seeing each generation give birth to the next set of people, and effectively, as we start to see these red people be born, these are the earliest people that are born who have parents, who in turn have had real parents within the population model. So we kind of like have this phased introduction of the population to the model. So yes, at this point we've had, and also at this point, because it's 50 years since the beginning of the pseudo-population, anybody in the pseudo-population age 0 is no longer able to have children. And then each 50 years, as I'm going to jump through, you will be able to see that more people that are useful for our real population by the time we get to time 250 exist, and that the volume of people in the population they represent is increasing as the earlier generations that are no use to us in our initial population die out. So we ultimately end up with a population which is fully made up of people with grandparents, and therefore at this point we can start simulation. So I'm going to move on now to talk a bit about how the actual simulation approach runs in the general sense once we actually start to run. So the orange bar we had at the end, which represents all the people, that has all the people in the population, is represented by this. And so if we imagine that we split this out into the females split by age and the males split by age, we can then start to perform things upon the population. So we have, so for example, with the death table I showed you before, we take all the males age 0. If we say we have 250 of these, we can find a rate at which males age 0 die in the next year, so which is risk given rate, and that then tells us how many people to die. So we then select 3 individuals at random from this first bucket to remove from the population. First thing that will jump to the forefront is the fact that we have rounding errors here that are existing, and we'll come back to discuss how we handle self-correction in a couple of slides' time when we've got a few other rounding errors that exist in the model. The other important thing to note at this point is actually we haven't considered anybody individually. We've considered cohorts and people born in a given year who have a given age. And therefore we're able to handle this process quite quickly. So if we move on to birth, so for example here we're considering we first need to find females to give birth to children. So if for example we take females age 20 from this bucket who have 2 children, we can then look up our value in the birth order table I showed you before, and this tells us that women age 20 with 2 children, the probability, the likelihood of them giving birth in the next 1 year is this, and so this gives us a number of women who are going to give birth. We also have the concept of separation, which is introduced in our model at this point into our model. So the idea, so we have 345 females, and we have a separation rate for women who have 2 children being separated by the time of the 3rd child being born. And therefore we can calculate a given number of females who need separating from husbands. So in this case, we select one female to separate. That means for 344 of these, we don't actually need to find a partner for them because that has been found in a previous year. So now to talk quickly about partnering. So here we're just considering the year of females that we've just been working with, and we have the one female who we've just found, but we've also got women from other birth orders who have had different numbers of children, so which will take to be a number of 350. Obviously, women having children for the first time will always need to have partners found for them. So we have this table, which is an extract from the table I showed you before, the birth orders. So these are not the birth orders, of the partnering table. So for women aged 20 to 24, the distribution of the ages of their partners. And then from this, we have 350 mothers, therefore the number of men of each age will be as follows. And then we have a process which flattens these down into solid numbers. So once we have these numbers, we can actually go and just from the sets of men, just remove the correct number, and then we're able to pair up all these chosen men with these 350 mothers in any particular way. It doesn't actually matter which way we do that, because whichever way we pair them up meets the statistical constraints that we have. Here we run into another potential issue, which is actually, say we've said there's going to be one man aged 50 to 100, and there isn't any men aged 50 to 100, that's another issue that we have. So if that was the case, we would end up taking somebody from here. But that again leaves us with an issue that we don't have the right number of people. So we have this approach called self-correction. So the idea of self-correction is when you go to the part of the program which stores these statistics, you go to it and you say, I need statistics regarding women getting the age of partners to women aged 20 to 24, and I will be applying this data to a given number of people. So you are given these statistics, and then you go away and you try and apply these statistics. You perhaps don't quite meet up to what you're expecting, so then you go back and you say, well, I applied these statistics to this many people, and the oracle in the middle of the program keeps track of all these different statistics that have been applied. So the next time you go and say, I'm going to apply this statistic to 200 people, the program, the oracle calculates a set of correction statistics which will bring us back to the initial statistics we were wanting to meet. And so there's this backwards and forwards inside the program which allows us to be kept very close to our actual statistics. So that's all going on as the population model's running. Once we get to the end, we actually want to validate what we're actually doing within the model has worked. So we have two validation approaches. The first that we use on anything that we call event-driven statistics, so the idea that this event will happen to an individual in the next year, is called Kaplan-Meier analysis. This is very similar to what you see in clinical trial research, and the idea we take here is we have a set of input statistics that we have given, and we can derive a Kaplan, which is in the form of a Kaplan-Meier life table. We get output statistics, and we can also create a table for that. So in a sense, we have two populations, and so we want to compare those two populations. Kaplan-Meier analysis is used in clinical trials where they also have two populations, or two or more populations, one with a placebo, one with an active drug. And they're interested in saying, are these two populations statistically different, significantly different statistically? Whereas actually we're interested in saying, are these populations the same population? So we're able to derive these tables for birth, for death, and also we'll be able to derive them for separation. When we plot these curves, so these are called the Kaplan-Meier survival curves. The idea is at the start, 100% of your population is alive, and as time advances, people die at different rates. And people die, and we get a curve that exists for that. We have have a line rep which represents what we asked for, and a line rep represents what we got, the real population. And then at the end of this, we get a p-value, or actually we get a very large number of p-values because we're doing this for many different cohorts of people over lots of time. The other approach we take is, or looking into taking, is doing an over analysis, an over comparison between two statistical inputs. So the idea here is, for example, partnering. Let's talk about multiple birth, far simpler. You have an input curve, so effectively for which we can train a regression. We define a regression model, and then so we have what we asked our model, and we have what our model actually did. For that, we can derive we can train two regression models. We can train one where we tell the regression model what the two different groups were, and we can train another regression model where we do tell it what the two different groups are. At that point, we can do an analysis of the variance between these two models, and we again get a p-value out to say, are these two curves statistically similar, or in the case of the example I put up, they're not. Okay, so then we have the question of how do we verify that the model we've made to make verified populations is actually doing what it's supposed to do in all different areas. So because we have inputs, even though we still only have 5 inputs now, there's a whole infinite different combination of inputs we could have. So we have a question of how we go about testing that model. So we derive the idea of having characteristics which would be plausible to have in a population. These are things like high birth rate or low life expectancy. And so by generating a matrix of these, or creating a matrix of these, we can then generate a whole range of input distributions that we can test our population using. Because we've managed to boil down the output of our population to a range of p-values which we can then consider and bring together, we can then say, without having to actually look at every individual model, has this model passed or has it not passed? And that means we have an objective correctness measure, so we can actually test the verified population model in lots of different ways. Another thing to note here is we're generalising this to different domains. We talked about having event-driven input statistics, which we can then evaluate to see if our model has mapped what the user has asked into its population. And so the idea here is that we have multiple different, we have these different input distributions, and they can be used for different things. They're not just tagged down to being used for birth or for death. So this is what we talked about, and so that brings us to how we generate this graph and how these different inputs and how we do the statistical analysis. What we do here is something we're currently working on, and something that we'll hopefully talk about in the future. So just to mention briefly other things that we hope to be able to apply this work to. An idea we've been talking about for a while is the idea of using it to generate synthetic data sets in privacy-sensitive environments. The idea that we take a set of summative statistics which aren't necessarily protected, and from that produce a reliable, realistic population, could mean that we actually can take data away from such safe havens. The other thought here is the way of using this for as an assistance to linkage. So as we've touched on a few times, what we're doing here is we're developing a way to evaluate our linkage approaches. Now, if we're given a set of real-world data we don't have knowledge of the true linkage of, we have the opportunity to take the summative statistics from that and to build a synthetic population. We're then able to run our linkage, to set up our linkage methods approaches to perform well on that synthetic data, which we trust, or we can say is similar to the real world data. Once we have set that model up to best perform, once we've set our linkage model up to best perform on the synthetic version of that real world data, we can then apply that linkage model to the real world data, and the question there would be, do we actually get better results? Thank you very much for listening. I think I'm just on time.
Great.
Any questions?
Excellent. And just a reminder, if there's people out there listening, and I think the recording or the streaming work, you can send me an email. Next 2 minutes, 3 minutes, if it arrives. Any questions from the audience here?
Presumably, when you create these synthetic data from summative statistics, as you called them, your synthetic data conform to the summative statistics, but not on things you haven't considered.
Yes, exactly. So the way
And I may be interested in things you haven't considered.
yes, exactly. So there's what I alluded to in the fact that we can the ability to generalise the model to potentially plug in different statistics to address the areas we're acutely interested in. And then the idea we mentioned with testing against secondary statistics, which is going to be something really interesting to see how well our models perform against. The idea of taking a set of summative real-world statistics, running a model with them, and then finding some other data from that, some other summative statistics from the real-world population that we've taken our summative statistics from, and seeing if that matches up. So the way in which we've engineered our approach, and that we've designed it in a sense to be a population model, we would expect that most of the things that would generally out there would match up with what you see based on the rules we have applied. But the question is, will they really match up? And that's what we're hoping to do with the secondary analysis.
Yeah, so just to follow up, yeah, I mean, it does seem quite crucial what the set of input statistics is, that if you want to get a model that's going to operate interestingly, that somehow you sort of fully identify the model in some way through the statistics. But I was actually going to just ask a much narrower question really, which is about how you mentioned these rounding errors, so that for me, in some ways, I was expecting slightly more stochastic simulation, so that when you say you get a population count which is 700 people of this kind, and then the proportion from the life table says it's 0.15 these, you then multiply the two and round it off. Whereas I would have thought more naturally, I would say, well, if we've got a binomial distribution here, and we're going to take the count as the n in the binomial and the proportion as a p, and then simulate so that it doesn't matter that n times p isn't an integer, and that you would then get a random number of people with this characteristic. But that would be treating it as, you know, the different people who have an independent chance of getting a birth or whatever the event is, given this population exposed to the risk of that event.
Would that, so that kind of idea of going from that perspective, does that lead you not to have issues when very, very rare events occur and the ability to bring them into the population?
Well, I would have thought it's even more important for very rare events, because if you get numbers which are less than 0.5, you're presumably rounding them off to 0. So, whereas if you stochastically generate them from the binomial distribution, you will occasionally get sort of ones and so on, occasionally zeros. So you will get some of those events happening. I don't know how you're dealing with it in your approach.
So that's where the self-correction things that I was speaking about come into that. So the idea that if you keep going back to the oracle and saying, I've not managed to do this, I've not managed to do this for this given set of people, eventually the likelihood of that happening when the correction statistic is returned will be increased to such a level that it will actually occur, but it will only happen very, very sporadically.
It doesn't seem to be like a stochastic approach. Like when you say I'm going to generate synthetic data, it's all about building, you know, some sort of multivariate distribution. Or I'm not, instead of just randomly selecting, I don't know, 20 people to die, there's usually a propensity for death, which is related to other variables. And you know, it doesn't seem to be that you're taking on, you know, any sort of
Any set of wider set of,
Yeah.
sort of, for example, occupation or
yeah.
things
So
like that.
synthetic data is you're building these multivariate distributions, and you're taking random draws, as Chris said, with the probability distribution.
Just to be concrete with Chris's question, does that mean, for instance, that your first divorce for someone with 3 children always happens after precisely 90 years for a certain population size, because you've built up a sufficiently large debt of people with that many children who haven't divorced?
So you would, so you would expect it to appear after. You could, so yes, I guess you could say you could deterministically calculate when that first divorce will occur, depending on how many people. But when I talked about in the presentation about how we selected the values for partnering, so we had a set of float values, and then we moved into a set of concrete values. The approach that we take there can sometimes vary and does have in the underlying distribution, the decision on which ones to take up and which ones to take down is dependent on a random selection process. And so you could, in that case, actually see slight variations, but there would be a set time frame and a set period of time you would see, I would assume, by having tested.
Okay. Tom's around the whole of next week, so maybe this room for discussion. I think your input is very valuable, right? Because, and you're coming back to the synthetic, hopefully synthetic workshop as well. Really great. Okay, thanks a lot. And I just heard from Robin that the streaming went well this time, so thanks a lot, guys. Fingers crossed it happens again next time when that would be. Thanks for coming. Thanks for coming.